Hello guys, welcome back. We are in part 2 of our pre-calculus full course series here at Forward Ed, and we're moving on to multiplication and division. So we'll be looking at the multiplicative identity, inverse, and properties of fractions. So we'll begin with the number 1. This is the multiplicative identity. A times 1 equals A for any real number A. So every non-zero real number, A has a multiplicative inverse, 1 over A, 1 divided by A. Zoom in there. Satisfying A times 1 over A equals 1. And division is defined as A divided by B equals A times 1 divided by B, provided that B is not equal to 0. And from there, we move on to properties of fractions. Let's zoom in on our visual. All right, we'll start with property 1. When multiplying fractions, multiply numerators and multiply denominators. And we'll go over this quickly because this is probably something you guys are quite familiar with. Property number 2. When dividing fractions, invert the divisor and multiply. Here's our example. Flip it. That's the reciprocal, right? Flip it, then multiply. Number 3, when adding fractions with the same denominator, add the numerator, simply keep that denominator. Number 4, when denominators are different, we find a common denominator, at least common denominator, ideally. Then we can add those numerators, as in our example here. Number 5, cancel common factors in numerator and denominator, as shown here. And then number 6, cross multiplication. A proportion means the cross products are equal. So in practice, guys, make sure that you find the least common denominator rather than just automatically using property 4. Which multiplies the denominators together, and it may yield a non-reduced result. Property 4, yes, it always works, but it may require some simplification afterwards. Now this takes us to example 3, where we're using the least common denominator to add fractions. So here we can factor each of our denominators into primes. We have 36 and 120 as our denominators. There we are, factoring each of those into their primes. You may have been working with factor trees before. That will help you with factoring into primes. But 36 is equal to 2 squared times 3 squared, and 120 is equal to 2 cubed times 3 times 5. Now from here, we can find our least common denominator, or in other words, the highest power of each prime factor. So for example, least common denominator of 2 cubed times 3 squared times 5 will get us to 8 times 9 times 5, which is equal to 360. Now we can rewrite with our denominator of 360. 5 over 36 will equal 5 times 10, which becomes 36 times 10, which will give us 50 over 360. And 7 1/20ths will get us to 7 times 3. 120 times 3 is 360 as well. Multiply that 7 by 3. After we multiply the 5 by 10 and the 7 by 3 for our numerators, this is where we end up with 50 over 360 plus 21 over 360 to get us to 71 over 360. Notice that after we use that common denominator, we go to property 3, adding fractions with the same denominator, much easier. All right, so again, we find that prime factorization of 36, which is equal to 4 times 9, or 2 squared times 3 squared. Then we move on to our prime factorization of 120, which equals 8 times 15, or 2 cubed times 3 times 5. Then we find that least common denominator from the prime factorizations by taking the highest power of each prime that appears. 2 cubed, 3 squared, and 5. So our least common denominator is 8 times 9 times 5, or 360. Now we're ready to write each fraction with a denominator of 360. 5 over 36, for example, 36 times 10, so 5 times 10, 50 over 360. We multiply the top and the bottom by 10. And then 7 over 120 will get us to 21 over 360 because we're multiplying the top and the bottom both by 3. Then we simply add our numerators together. 50 plus 21 equals 71 to get us to 71 over 360. Now, we can check, does 71 over 360 reduce further? No, because the only factors of 71 are 1 and 71. It is prime. So since 360 is not divisible by 71, the fraction is now fully reduced. All right, let's go to the real line. That's our next section. Here's our real number line. Choose an origin of 0 that, it will correspond to 0. Right in the middle. Then from here, we can understand our properties of our number line. To the right of the origin will be positive numbers. To the left of the origin will be negative numbers. Each point P has a coordinate, its real number value. And then for order, A will be greater than B if A is to the left of B on the number line. Or I'm sorry, less than B. A will be less than B if A is to the left of B on the number line, and A will be greater than B if A is to the right of B. So let me give an example there. For example, -5 will be less than -4.9. As we're considering absolute value from 0, -5 is further from 0, going to the left, so it's less than -4.9. -pi will be less than -3. The square root of 2 will be less than 2. Four is less than 4.9999. And so forth. All right, so the real number line here is a visual model for all real numbers. Every single point corresponds to exactly one real number, and every real number corresponds to exactly 1 point. The position tells us the size, points to the right are larger. So why would you plot -pi on the number line? Is it between two integers? Since pi is equal to 3.14159 approximately, -pi will be approximately equal to -3.14159. So it lies between -4 and -3, specifically just below -3 to the left of -3. All right, where would you plot the square root of 3 on the number line? Since the square root of 3 is equal to approximately 1.732, it will lie between 1 and 2, but closer to 2. Now, require decimal approximation for all irrational numbers before attempting to plot them on the number line. This is non-negotiable. Students often have difficulty placing irrational numbers. So, compute the decimal approximation first to at least 2 decimal places, then locate the position between the known integer or decimal benchmarks. All right, let's go to sets and intervals. That's our next section. All right, so sets are the language used to describe collections of numbers precisely. Now, we already know sets from everyday language, like a set of dishes, a chess set. Mathematical sets are the same idea, but with exact membership rules. For example, if z is the set of integers, is -3 an element of z? Is pi an element of z? And the answer is yes, -3 is an element of z because -3 is an integer. But no to pi. Pi is not an element of z because pi is not an integer. Now, a union means all elements in S or T or both. So list every element that appears in at least one of the two sets with no repeats. Now we'll move on to example 4 for a union and intersection of sets. A union just means all elements in S or T or both, and we'll list every element that appears in at least one of the two sets with no repeats. Let's take a look here at example 4. So we'll let S equal 1, 2, 3, 4, 5, T will equal 4, 5, 6, 7, and B will equal 6, 7, 8. So we want to find A, all elements in S or T, B, elements common to both S and T, and C, S and V, common elements. Let's look at a visual of that here to the left. So which elements are in S or T? 1, 2, 3 are only in S. 6 and 7 are only in T. Four and 5 are in both. Union contains all of them. So let's write that out. Now the brace looks like a little bird there, right? And there's our answer. For A. What about part B? Now, intersection means elements in both sets simultaneously. So in other words, which elements appear in both S and T? Let's zoom in, 4 and 5. So let's write that out for B. Upside down U. And another brace set for 4 and 5. There's our answer for B. And now C. Which elements appear in both S and V? So S is 1, 2, 3, 4, 5. And V is 6, 7, 8. So there are no common elements. We can write that down. There are no common elements, written here as well. So let's go ahead and write that S with our upside down U, V now. Put a line through that 0, a slash through the 0. The empty set. S and V have no element in common. Now keep in mind that the empty set with the slash through the 0 is not the same as 0 in a brace set. The empty set has no elements. Now the set 0 has exactly one element, the number 0, right? So this distinction matters when you encounter empty intersections. All right, we'll go ahead and call it an end here to this part 2 video. And in our next part, we're going to jump into intervals. See you soon.